welcome to the 22nd lecture on electronic circuit design. In this lecture, we will study biasing class AB Push Pull Amplifier. In our last lecture, we studied that there is a crossover problem. This problem is very common for class AB Push Pull amplifiers because the input because the output voltage is delayed, it doesn't start increasing unless the input voltage crosses 0.7 volt. Why is this? Because there was no separate biasing and the input AC signal, the same input AC signal is used for biasing. The input signal is also serves the purpose of biasing. Actually, that is why we have this distortion, this crossover distortion. We studied this crossover distortion and the reasons for this distortion in our last lecture, ECD21. So in this lecture, we'll study a very simple technique to combat this problem. How can we handle this distortion, this crossover distortion that we get in every half cycle using two diodes, D1 and D2. This is the difference between the circuit that we studied in last lecture and in this circuit. The difference is these two diodes, D1 and D2. Let's see what's the purpose of these two diodes. These two diodes, they work, for example, let's start from here. So it is 0 volts, it's RL, the other side, the lower end of this RL is connected to ground. This means the upper end is 0 volts. So if it is 0, it is at 0 volts, the space voltage has to be at 0.7 volts, right? 0.7 volts. And this also connects to the anode of the diode D1, and the cathode is what should be the voltage of cathode if this diode is also on? Of course, 0. So we get a 0 volt here. So we get a DC 0 here, a DC 0.7 volt here at the anode of this diode and at the base terminal, and a 0 volt here. So that's straight. Why? Because this 0.7 volt is already available. Even if we haven't connected this AC signal, this terminal, the base terminal, is at 0.7 volts higher than ground. This terminal is at ground. So this means that as soon as we apply a voltage that is as small as, for example, 0.1 volt, a very small input voltage, that will take the voltage of the anode of this D1 to 0.8, and it will find the junction on. And 0.8 minus 0.7, the 0.1 volts voltage will be available at the output. So what's the purpose of this diode D1? During positive half cycle, we get the output right as the input increases above 0, just above 0. This means there is no crossover distortion during positive half cycle. So this D1 avoids, with the help of D1, we avoid crossover distortion in the positive half cycle. And with this diode D2, we avoid the same distortion during negative half cycle. This is because we get a biasing of 0.7 volt all the times here, and a biasing of minus 0.7 volts all the times here, helping the output to appear as soon as the input appears, the input voltage appears. So there is no distortion. We don't have to wait until, otherwise, if we don't connect D1 and D2, we have to wait unless the input rises itself beyond 0.7 volt during positive half cycle, or it falls below 0.7 volts during negative half cycle. So actually we have avoided this crossover that we discussed in last lecture. How? With the help of D1 and D2. So D1 and D2 are closely matched. These R's are always equal, R1 and R2, and point A is at a virtual ground. What does this mean? A virtual ground. Virtual ground means this is the point which has a voltage 0 volts, but it is not actually connected with the second ground. So how would we obtain this virtual ground? It's not directly connected to ground, but its potential is exactly equal to the potential of the ground. Why? Because this voltage is 0, DC voltage 0 volts. This voltage is 0 plus 0.7, and since this is the voltage of the anode of this diode D1, the cathode will be 0.7 lower, so that would be 0. So it is 0, but it's not actually connected to ground. That is why it's not exactly actual ground, it's virtual ground, fake ground. And V out DC, of course, is 0 volts if we haven't supplied any. Right, even if we have supplied this V input, the DC voltage is at 0 volts. So we have a good reference 0 volts here. That is why we don't need a coupling capacitor. This is another reason we don't have an input coupling capacitor and output coupling capacitor, because the DC voltage at the output is always 0 volts. So we don't need any coupling to stop the DC voltage from appearing at the output. So Q1, Q2, D1 and D2 are matched. Q1 and Q2 are these two transistors, D1, D2 are these two diodes, and R1, R2. So everything is matched. Q1 matches Q2, D1 matches D2, R1 matches R2. So VD1 is VBE1, this base emitter voltage. This is the same point VBE1. This is exactly same as VD1 because the other end emitter is grounded. Here we have this virtual ground here. So this voltage is the same. The voltage of the anode for diode D1 is the same as the voltage of base, or the voltage of between base and an emitter, because emitter is grounded for DC. And VG2 is VBE2. Therefore, it's a current mirror. What does a current mirror means? It's a current mirror. This means that if we just look at this circuit, if we just look at this part of the circuit, it is a current mirror. How is it? Let me explain. If we just look at this part of the circuit, so we have this current flowing. These two diodes are matched. The current that flows into the ground and the current is negative, and this negative current that flows into, and this current flows into from collector to emitter, from this diode to, from the anode of this diode to the cathode of this diode. So this means there is a path of current. It is actually a path of current, and since this is the path of current, the current should be the same. This is only one circular path of current, so it should remain the same, right? So how would it be? What should this current be? In this path the current should be the same, but what would be the exact value of the current, right? Let's try to find this out. Assume that the voltage here is VD. Assume the voltage at this point is VD, and of course this is 0.7 volt because this voltage is greater than 0.7, greater than the voltage of emitter, and the voltage of emitter is ground. So this VD is 0.7. So what would be the current flowing through R1? That would be VCC minus the voltage here divided by R1. So VCC minus VD over R1 is the current flowing through resistor R1, and the current flowing into the terminal is the same. This current, and this current, these two currents would be the same, and that we can compute using VCC minus the voltage here divided by R1. So VCC minus VD, which is 0.7 divided by R1, is the ICQ. This current flowing in this collector or flowing in this collector. Or flowing in this collector. So in both collector terminals we have the same current. ICQ, that is equal to VCC minus this voltage drop divided by R1. So we want to change the current IC here. Why is this circuit called current mirror? Because we cannot control this current IC, this IC and this IC directly, but we can change it by changing R1 and of course R2, because they have to be the same all the times. So if we change R1 and R2, we can vary the current flowing through this resistor, and of course, and the same current flows through this IC. So IC can be IC can be controlled using this resistor by making this R1 variable. So we don't actually make this variable because we set it once, and that sets the value of IC. So IC is dependent on, in other words, the IC, the collector current, is dependent on the current that flows through R1, that flows through R1 and R2, or in other words, is dependent on R1 and R2, the values of R1 and R2. So if VBE is, and we know that VBE is inversely related with temperature. So if increasing temperature will increase VD and VBE. Right. So as VBE decreases, because increasing temperature will increase VBE, as the heat increases, VBE, or the temperature increases, VBE decreases. So if VBE decreases, ICQ increases. And next lecture we'll see that this has no, in this same lecture we'll see this has a positive, it's a vertical DC load line. This kind of power amplifier has a vertical DC load line. Either we have a constant current ICQ, and if it increases due to thermal imbalance, it increases vertically as a vertical line. We'll see that. So increased ICQ causes permanent failure because the current increases without bounds. We'll see how. So avoiding crossover distortion is possible even for this transformer coupled circuit by initially we set this to ground. When we studied the first time, we set this voltage to ground. So now we don't set it to ground, rather we set it to a voltage that is 0.7 higher. So why? To bias this at 0.7 volt DC, so that this junction is on all the times. As soon as we apply AC voltage, it will find this base emitter junction on all the time. So we don't have any crossover distortion. Well, whereas the remaining circuit is the same, and IC sat is also the same, VCC over RL, that we studied earlier. So the DC load line is vertical. This is amazing. This is unusually amazing. This is a vertical load line. Why is this vertical? Because ICQ is a constant current, and if it increases due to thermal imbalance, so resulting in a permanent failure. So this increase in current is due to thermal imbalance, or we call it thermal runaway. So this is due to thermal runaway. Otherwise, we have a constant current ICQ as long as the temperature is within limits. So lastly, we have an example where we have R1, R2, D1, D2, and an RL. So values are given for R1 and R2, they are always the same, and this RL. So what we are asked to find two quantities. V out is the max V out, VCEQ, that is of course 20 volts. This is the max output that we can get, that is approximately 20. Why 20? Because it works in this region, so it amplifies only one portion of the input, so it can take on all the way from 0 to VCC. It can take this whole range, because you don't have to amplify the other half cycle. So since we have to work only in this half cycle, in one half cycle, so we can take on all the range from 0 to VCC. So VCE max can be, VCEQ is 20 volts, because because the amplifier is biased very close to VCC, very close to VCC. We studied that in last lecture. It's biased very close to VCC. Q point is very close to VCC, and we have a very small current flowing. So it's near cutoff. So IC sat is VCC. This is the max IC, ACIC. This is AC. ACIC that can flow through. IC sat is the max IC. So the max IC would be VCC over RC. VCC over RC, assuming that VCE is approximately equal to 0 volts. There is no VCE. So there is no VCE. VCE is approximately equal to 0. VCE here, VCE is approximately equal to 0. So when we have approximately 0 VCE, we get maximum IC. The transistor is in saturation. SAT. The SAT means saturation. This is saturation. We say VCC over RL is 1.25. So that's all for this lecture. What we have studied, let me summarize. We have studied, actually we have solved a problem of crossover distortion that we encountered in last lecture. So we have solved this problem using these two diodes, D1 and D2, that bias the base emitter junction, and they turn this base emitter junction, this base emitter and this base emitter junctions on all the times. So the same is possible for transformer coupling, and we have studied thermal runaway due to temperature changes, and we have solved the problem. In the next lecture, we will study the same push-pull amplifier but for single supply. Up till now, we have been studying circuits that have dual supply, this plus 20 volt and minus 20. So in next lecture onwards, we will study the circuits where this would be a ground instead of a negative VCC. Right, that's all for this lecture. Thank you.